All right, so let's go ahead and share. All right, so the other day you started to look at writing formulas. Obviously, we were watching from a different perspective. It wasn't me. So I just want to touch base, review, make sure we're good to go, okay? So that if I said hydrochloric acid versus chloric acid versus chlorous acid, that you would know what we're talking about, okay? So your hydroic acids. So you only use the prefix hydro when you are putting it with something that ends in IDE. I think an even easier way to think about that is just when it's with a non-metal. Okay, so whenever you have a non-metal, that is what is going in as the hydroic acids. Okay. So hydrofluoric is with fluorine, hydrochloric, chlorine, hydrobromic, bromine. Okay, so whenever you have those nonmetals, that's what's going on there. And then remember, whenever you have an acid, your cation is always going to be hydrogen. Okay, so as soon as you see the word acid, think hydrogen. Okay. Then we had just the plain ic acids. So hydrochloric versus chloric. Okay. So when it is just an ic acid, that is from your ATE polyatomics. Your ATEs. So our ATE list is a lot longer than our ITE. Okay. So just keep that in mind. There's definitely more for us, not in the world. For this class, there are going to be more ics than us. Again, because you're dealing with an acid, when you're writing the formula, you've got hydrogen first. Okay. So what you see there is a little slogan to sort of help you keep in mind which ending goes with which. Again, if you are not a slogan person and you just want to memorize stuff, go for it. But if I can give you a cheesy way to memorize something, I'm going to do it. So if you ate something that made you sick, okay, so if you ate, ATE, something that made you sick, IC, your 8 polyatomic ions become your ic acids. Okay, 8 made you sick. Go with it. Hang on. Okay, so that sulfuric acid is using sulfate. Something else I want to point out here, right? So we say that when you're doing this, you take off the ATE and you add ic. So technically, right? So just take a look for a second. Technically, sulfate, right, would become sulfic. If you wrote sulfic acid on a quiz or a test, I would give you credit, okay? Because you were doing the correct thing. You took off the ATE, you made it IC, fantastic. Scientists think that it sounds like it sounded weird, sulfic. And sulfus is the one that's really hard to say. Okay, so sulfus acid sounds a little bit ridiculous. And so they put the UR back in to make it flow. Sulfuric acid, sulfurous acid. Again, if you wrote sulfus, I'm going to give you credit. Okay, because you're following the rules. So I just wanted to point that out. The same thing happens for phosphate. Phosphorus is a weird word. So they make it phosphorus acid. Phosphic versus phosphoric acid. Again, no biggie, whichever you write. I'm just letting you know, and I'll correct it so you're learning it correctly. But it's not a big deal in terms of spelling. Okay. So if you ate something that made you sick, the other ridiculous part of that is that you might give it to us. Okay. So your ite polyatomic ions become OUS acids. So these OUS, these are your ite polyatomics. Now we had far fewer of these. We had nitrite, sulfite, chlorite, hypochlorite. That might be it. I feel like there's probably one more, but not many. Okay, so shorter list. But again, notice it's sulfurous acid instead of sulfus. Okay. We also, I talk about all the time in chemistry, like I hate taking off points for spelling, but spelling obviously matters. So when I say phosphorus versus phosphorus, can you tell the difference? If I say phosphorus or if I say phosphorus? Right? Like those sound exactly the same. OUS versus US. Phosphorus US, total stable element. Phosphorus OUS, an acid. Not so safe. Okay, so paying attention to these little spelling things, right? Like could be super dangerous. So just to make sure we're all good, I want you guys to take a quick moment and just go ahead and do these practice. So on the left, you are writing the formulas. On the right, you are naming them. Yes. Okay, so some strategies that I would use when I just had like a list like this, okay, was I might take a second and I would note the different naming rules, meaning this says hydroic, this is just ic, this is just us, this is just ic, and this is hydroic. Okay, so by taking that time, I know that my hydroics are with nonmetals, and ic, if you ate something that made you sick, you might give it to us, right? Okay, and so you can kind of think back. So my thought process would be, okay, so for all of these, obviously they're acids, but when you get to your your final exam, obviously not every question is going to involve an acid. So a good thing to just, come on, guys. When you see the word acid is to take a minute and write H plus, H plus, H plus, H plus, H plus, right? As that, like, okay, that's what the cation is. Then hydrobromic came from bromine. Bromine is -1, so HBr. Phosphoric came from what? Phosphate. PO4 -3, so it's H3, PO4. Chlorus came from what? Chlorite. Good, right? You might give it to us. You might give it to us. OUS chlorite. ClO2 -1. HClO2. Carbonic came from carbonate. CO3 -2. So H2CO3. Hydrochloric came from the nonmetal chlorine. Chlorine has a -1 charge. HCl. Any questions about any of those, friends? Right, I mean, these are pretty easy in terms of writing formulas. Your charges for your anion is always your subscript for your cation, because you're just multiplying your hydrogen by however many you need. Because it's hydrochloric. Okay, yeah. So I always like to take a note and kind of circle those hydros, because they definitely, good morning, they definitely sneak in. Yep. For sure. They definitely kind of sneak in with those X. All right, so then on the right-hand side, these we are naming. So just look at your anion. So ClO4 is perchlorate. Oh, I'll put my pen down. So perchlorate, if you ate something that made you sick, perchloric acid. H2SO3. SO3 is sulfite. You might give it to us. Sulfite becomes, again, if you write sulfus, cool, give yourself credit. I'm going to write it correctly. Sulfurous acid. H2S, that's just an S, right? There's no oxygens involved, okay? Just an S, so that's our nonmetal. So that's where we're going to use a hydrosulfuric acid. And then PO3 is phosphite. You might give it to us. Phosphorus acid. Again, if you wrote phosphorus, give yourself credit. Okay? All right, so hopefully we feel good about that. But I did want to take time to retouch on it. Okay, so let's talk about acids. All right, so acids are everywhere. You're interacting with them all the time. Okay. There you've got an example of your fruit. So what makes an acid? An acid is going to be that hydrogen ion. Okay. A hydrogen ion. A hydrogen ion. So let's think about some of the properties of acids. When you bite into a lemon or a warhead, what do you notice? Sour. Okay. Their main ingredient is citric acid. Okay, so acids are definitely going to be sour. Acids are sour. This doesn't make total sense yet unless you're familiar with pH, but I want to have it all in one place so that when you're studying for your test, it's all in one place. Okay, pH is our next class. But for acids, they're going to have a pH less than 7. pH less than 7. And they are going to give off hydrogen in reactions. Acids are going to give off hydrogen in a reaction. All right, so let's talk about bases. So bases, we're going to kind of have two defining moments for them when in terms of what makes a base, and that's what kind of today's class is looking at these two differences in bases and acids definitions. So what makes a base is that it's going to contain hydroxide. Okay, typically a base will contain hydroxide. Or they take a hydrogen from the acid. Okay. So they're either going to contain hydroxide or they take hydrogen from the acid. Okay, so have any of you ever had your mouth washed out with soap or accidentally tasted soap or bubbles by mistake? Okay, that's maybe more realistic if you haven't had your mouth washed out with soap. My grandmother used to do it to me all the time. Hard to believe I talked back to my mom, I'm sure. So if you've accidentally tasted soap or had to taste soap as a form of punishment, how would you describe it? Bitter. Very good. Bitter. Bases are bitter. Okay, bases are bitter. Please don't go home and eat soap. Please don't eat soap. I had to do it for my chemistry homework. Yeah, they're bitter. And how else? So when a bar of soap gets wet and you're trying to hold it, how would you describe it? Slippery. Yeah, bases are also slippery. So if you've ever like walked around in the French Quarter or there's like cobblestone sidewalks after it rains, they're like very slick. Yeah, that's because they contain bases. So there you go. Fun facts. What else about bases? They're gonna have a pH greater than 7. Again, doesn't make sense yet, but it will. Okay, they're gonna have a pH greater than 7. sounds good for now. So what you see up there, that little picture I included, says "an" acid. Any Latin folks in here, or do you just know what the prefix "an" means? Really? Not. Yeah, so the word "antacid" means not acid. Okay, they're very creative, like Tums, Pepto-Bismol, all that stuff that you take when you have a stomach ache. We're going to study neutralization reactions after the halfway quiz. But the way those medications work is when you have a stomach ache, what lines your stomach or what's in your stomach is stomach acid. When that acid gets unbalanced, like if you've ever had a little bit of acid reflux or gnarly burp, or if you've had a stomach bug, right, it kind of burns, it's because of all the acid in there. You're going to take an antacid, a not acid, aka a base, to sort of neutralize that out. So when you mix that acid and a base together, you get a neutralization reaction. So definitions of acids and bases have changed over time. There's multiple definitions out there. We're focusing on the two main ones. Okay, so again, if you look up acids and bases online, please know there's going to be more information than you need for this class. Okay. So the very first kind of look into acids and bases was this guy Arrhenius, is how you say that. Okay. And so he kind of first studied trying to see what was happening with, excuse me, with acids and bases, what made them different, things like that. Okay. His definition of an acid was in water. In water, acids will lose hydrogen. And for bases, in water, they were going to lose hydroxide. So at this point, the definition of what the base was that it had to have hydroxide. That's an awesome point. So that's the overall. This is the Arrhenius definition. Okay. So Arrhenius was like, great, acids have to have hydrogen, bases have to have hydroxide. That was where it started. That was what we looked at. He broke down acids a little bit further into categories. Monoprotic, diprotic, triprotic. Mono, di, tri. We know that. What does that mean? Yes, 1, 2, 3. Right? 1, 2, 3. Protic, think about it. You're in chemistry class. What does that make you think of? What word that you've like heard of in this class that's similar to protic? Proton. Very good. Okay. If you think back to a proton is the same thing as a hydrogen. Right? When we were studying them, we were like, okay, they have a mass of 1, a +1 charge. Hydrogen. So a monoprotic acid is going to contain 1, I'm going to put a word in here and then I will explain it. 1 ionizable, just write it down. I'll write it down since it's a new word. Yeah. 1 ionizable, not a cool word. Okay, 1 ionizable hydrogen. Right, so the suffix able means ability. Right? You guys been up here for a rainstorm? They're pretty loud. Okay, so a ionizable means the ability to lose an ion. AKA here we're talking about hydrogen. So as fancy as that word is, it basically means it can lose 1 hydrogen. Okay, that's what that means in like common language. A monoprotic acid is going to lose 1 hydrogen. So some examples of that, right? Like HCl, HNO2. Now, acetic acid, which is also just vinegar, FYI, is C2H3O2. So you might look at that and say, well, there's 4 hydrogens. Those hydrogens in the middle, the H3, that's part of acetate. That's part of your anion. That is not those hydrogens are not ionizable. Okay, just these friends in front. So diprotic acids, what do you think it means? Nailed it. 2 ionizable hydrogens. So in English, what does that mean? It can lose 2 hydrogens. Very good, Mai. Right? It can lose 2 hydrogens. Either Ty or anybody in class, why don't you come up with an example in your notes for a diprotic? Think about something that could lose 2 hydrogens. Yeah, Landry? Sulfurous acid, very good. Ty, my man, do you got one? No, that's okay. Yeah, Hunter. It's not going to be hydrocarbonic. There we go. Carbonic. Yeah, Ty.
Hydrosulfuric acid.
Very good. All right, so whenever you're going to have those little 2s, you could have done dichromic acid, chromic acid. There's an example that often comes up from students here, H2O. Anybody seen that before? Fun fact about water, we're going to study it in about 20 more minutes. Okay, H2O is a lie. That formula that you've learned your whole life is a lie. It's not how you write water. Okay, I'm just going to blow your mind today. It's going to be great. So triprotic acids, what does that mean?
3.
Hey. 3 ionizable hydrogens. 3 ionizable hydrogens. Our examples here are much smaller in terms of the list. You got your phosphates and your phosphites. Can you hear me back there, Ivy, with all the rain? Yeah. We got 2 from the periodic table, hydronitric and hydrophosphoric. That's kind of it. All right, so taking a look at his reactions. When you look at this thing, this is not something you'll ever have to draw or anything like that. I just wanted a visual component. Y'all, that was an incredible lightning strike behind you. Oh, I feel like we should learn that way so you can see it. Okay, yeah. Yes, we're gonna finish Arrhenius, so it's like 2 more slides, and then we're taking a break. So when you look at this here, you can see the way this hydrogen, when dissolved in water, came off and attached itself over here, right? You can see that the H2O became H3O plus. We're going to see this a lot this unit, so go ahead and highlight it, circle it, whatever it might need, whatever you might need. Something called hydronium. It's a very cool thing. When I blow your mind about the formula for water. Sorry, this lightning is just wild. When I blow your mind about the formula for water, we'll talk more about hydronium. All right, so here's a look at sodium hydroxide. When it dissolves in water, that hydroxide is breaking off. Okay, so just as a reminder, when you're talking about Arrhenius bases, the key word that you want to keep in mind is hydroxide. Okay, because this is going to be the main difference in our next definition. All right, so it is 10:40. We're going to start back up at 10:45. Watch that way if you're taking a break. So Ty, 5 minutes, okay, bud? You may. Okay, so our main difference, when we talked about Arrhenius, we said that in water, acids were going to lose hydrogen, and in water, bases were going to lose hydroxide. Okay, that was Arrhenius's definition. But then as time progressed, people noticed that other things were acting as bases that didn't have hydroxide. So you know that saying that all Kleenex are tissues, but not all tissues are Kleenex? Do you guys know that saying? Like Kleenex is a brand. So like all Kleenex are tissues, but not all tissues are Kleenex, right? You can have other brands of tissues. I know that seems like a really far-fetched way to talk about bases, but things that contain hydroxide are bases. But bases can also be other things. So all bases contain hydroxide, but not all bases. Anything that contains hydroxide is a base, but bases can be something else too. In the same way that all Kleenex are tissues, but not all tissues are Kleenex. Maybe I missed on that one. But the Bronson-Lowry theory agreed and said acids donate hydrogen. Okay, so the Bronson-Lowry theory of acids is an acid is defined as a substance that can donate a hydrogen, or not a hydrogen, can donate hydrogen. That's for acids. Similar idea, but notice it doesn't involve water anymore in the definition. Okay, we don't need water to make this happen. Right? Acids can donate hydrogen, and a base is a substance that can receive a hydrogen. So sometimes you'll see this simply listed as an acid is a hydrogen donor, and a base is a hydrogen receiver. Receiver, I before E. Okay. Again, can't spell common words, just really fancy chemicals. Okay, so hydrogen donor, hydrogen receiver is like the simplest way. Okay, and they're going to go hand in hand. That's the other key part of this theory, is that the acid donates a hydrogen and the base receives it. Okay, so they kind of go together in a pair. So looking at this picture here, we have NH3 and we have H2O. So when we look at these things, it can be kind of hard to decide what's our acid, what's our base. So we're going to practice with this, not to worry. But reminder, acids are going to lose a hydrogen and a base is going to gain a hydrogen. That's our kind of like key, or you can use the word receiver, donor, acceptor, whatever. So when we look at this thing, NH3 goes to NH4. Did it lose a hydrogen or gain a hydrogen? It gained. So by the definition, that makes ammonia a base. NH3, when it went to NH4, it gained a hydrogen. Whereas when you look at H2O, it became OH. So when it did that, it lost a hydrogen. Notice that every time I'm writing hydrogen, I'm not writing just the letter H. What else is there? H plus, right? Because a hydrogen ion has a +1 charge. So when it loses that hydrogen, or when it gains a hydrogen, it's also losing or gaining a charge. So you can see that NH3 went to NH4 plus. So not only did the 3 become a 4, it went from a neutral to a positive charge. H2O went to OH. Don't write HO. Okay. And now it had a negative charge. So it loses the letter and the charge. What if something can do both? So we're talking about what if something can lose or gain. Okay. This is something called amphoteric. And it can act as an acid and it can act as a base. So all your life, you have been writing water as H2O, which is great because it's simplified. Water is actually HOH. Okay. Water is HOH. And so a lot of times, whether you've taken chemistry or not, people talk about water being neutral. Is that something a lot of you have heard before, that water is like neutral? Okay. So, and again, we'll talk about the pH scale next time, but water has H, which makes it an acid, and OH, which makes it a base. So the reason that, hey, that water is neutral is because it's H, OH, acid, base. It has the ability to either lose that hydrogen or gain hydrogen. It's kind of, I mean, it's pretty cool when you think about it. So if you think about water as H2O, the world that you have been raised in, as an acid, what does it mean to be an acid? Gives hydrogen. What will that formula become? If H2O loses a hydrogen, what will it become? Very good. Please do not write HO. You are chemists at this point. It is not HO, it is OH. And when H2O acts as a base, we know that that means it's going to gain hydrogen. And this forms a really important thing called H3O, which you're going to see a lot of, like I mentioned. So H2O became H3O. But remember, it's gaining a hydrogen ion. So while H2O is neutral, when you add a hydrogen, that charge also goes up. So we have some terminology for these things it's creating, this OH versus H3O. Conjugate acids and conjugate bases. I'm going to give you the definitions. They're going to seem like the opposite of what they should be. And then I will explain why. A conjugate acid is the product formed. A conjugate acid is the product formed when a base gains a hydrogen ion. It is the product formed when the base gains a hydrogen ion. Your conjugate base is the product formed. The product formed when an acid loses a hydrogen ion or gives off, donates, whatever. So like I said, I feel like those definitions sound like the opposite, right? Like a conjugate acid is formed by a base. A conjugate base is formed by an acid. Let's talk why those words are what they are. If you look at the example, well, there's two, but let's just look at the first one first because it's first. We know that the definition of an acid is that it donates a hydrogen. So when we go from H2O to OH, we can see that it lost a hydrogen going that way. Yes? Went from H2O to just one H. That is the definition of an acid. Loses a hydrogen. When you look at this reaction, going from OH to H2O, what did it do? Going from OH to H2O, the red arrow. What's the difference? It gained a hydrogen, and gaining a hydrogen is the definition of what? No, not that. What did we say? I've said it multiple times, right? Gaining a hydrogen is what? An acid or a base? A base. That is why it's called a conjugate base, because when the reaction goes the other way, it's acting like a base. So when you read left to right, H2O acts as an acid. It loses a hydrogen. When you read right to left, OH goes to H2O. So the OH is acting like a base. That is where those names came from. Right? Because often these reactions can go both ways. So when you're reading left to right, the stuff on the left is either gaining or losing, but you can also look the other way and something gained or lost. Okay? So that's where that terminology is coming from, whether you're reading left to right or right to left. So when you look at this next example, oops. Let me go here. When you look at HCl going this way, HCl became Cl. Did it lose or gain a hydrogen? That's the definition of an acid. When you look right to left, Cl becomes HCl. Did it lose or gain a hydrogen? Gained. That is the definition of a base. Okay. All right, so what you can see in this example down below of ammonia reacting with water, something called a conjugate acid base pair. That is represented by that blue line. Your acid is always paired with a conjugate base. Your acid is always paired with a conjugate base. And the base is always paired with a conjugate acid. The acid is always paired with a conjugate base. The base is always paired with a conjugate acid. That's literally what that blue line is showing. So this is a skill that you will need to do for this unit. You will need to label bases and acids. You will need to label conjugate acids and conjugate bases. And you will need to show the pairing with those blue lines. Okay. So you have an example here, 2 examples. I want you to label what's your acid, what's your base, what's your conjugate acid, what's your conjugate base, and then show the little pairings. So think about what the definition of an acid is, what the definition of a base is, and go for it. You got this. Okay, So when we think about an exercise like this, it can be helpful to break down those terms again. So reminding you that acids are going to lose hydrogen. Bases are going to gain hydrogen. Conjugate acid is a product, or a base product, I guess we could say. And our conjugate base is our acid product. So when we look at this, we have CH3COOH. It becomes CH3COO. It lost a hydrogen, which makes this acid. And this, your conjugate base. H2O became H3O, so it gained hydrogen, making this your base, this your conjugate acid. We show our pairing with the little brackets. Any questions about that first one? Okay. Oh, golly Moses. Looking at the second one, HNO3 became NO3 minus. It lost a hydrogen, which makes it the definition of an acid. And the NO3, your conjugate base. OH became H2O, so it gained a hydrogen, making it the definition of a base. So this is our conjugate acid. And then we pair it up. I listed them in the same order. Oops, oh well. Okay, so that's one thing you'll need to be able to recognize. The other thing that you'll need to be able to do is if I simply say HNO3, what's its conjugate base? So without having the whole reaction there to look at. So let's practice that now. Okay. So before we go through this, I do want to give some reminders and some things to look like what you're going to do. Okay. So our definition of an acid, right, was that it's going to lose, donate, give, whatever word you want, right? Lose a hydrogen ion. And we keep saying this. I keep saying losing a hydrogen ion, losing a hydrogen ion, right? So you're literally going to take away the letter H, right? H2O became OH. We took away the letter H. And then the charge, you can't ignore that piece. Okay, the charge goes down by 1. Right, because hydrogen has a +1 charge. So every time you take away a hydrogen, you are taking away a positive thing. Whereas when we talk about a base, right, we said that they are going to gain a hydrogen ion. So you're literally going to add the letter H, right, H2O, H3O. And now the charge goes up 1. So if I gave you the acid HCl, right? So if you look in this table, if I give you the acid, HCl becomes the base, Cl. I took away an H, and I took away a charge. If I was going the other way in this table, Cl minus is my base, If I had a blank on the left going from base to acid, I would add a hydrogen. So what this table is asking you to do is fill in the other side. So if I give you the base, I want to know the acid. If I give you the acid, I want to know the base. Okay. So give a shot, and you can talk to each other if you want to, whatever works. Filling in this table based on what I give you and based on what we just talked about, right? If you're going from a base to an acid versus an acid to a base. And again, feel free to chit chat. Grab some water. Woo. So nice to be cold in here. All right, so I'm going to do the first two so we can make sure we're on track and if you need to go back and make changes. So the next one I give you water is H2O, and I'm telling you that it's a base. Definition of a base is that it can gain a hydrogen. So I need to add a hydrogen to the formula, H3O. And I also need to make the charge go up. It was neutral, so now the charge becomes positive. HSO4 minus, I'm telling you that it's an acid. The definition of an acid is that it's going to lose a hydrogen. So I take it away, and it's SO4. The charge was negative. I then lost another one, so it became -2. I saw a couple changes happening, so I'm going to give another 30 seconds or so if anybody wants to make any other edits real quick. So in that next example, which hydrogen do you think it loses? The one on the end. So I'm going to write it the way it's listed here, but I'm going to also show you. Can anybody recognize what that is? It's just acetate. Okay. If you go on to take organic chemistry with me, either your junior or senior year, we write things out kind of the way they are as a molecule. So like when that's attached, there's like a carbon with hydrogens attached to it, then to another carbon, which is attached to an oxygen, which is attached to an oxygen, which is attached to hydrogen. You write them the way they are as molecules. So fun fact. Okay. I think it's fun. So for the next couple ones, HC3O3 as a base, that means it's gaining. So it becomes H2CO3. It was -1. It gained a positive charge. Therefore, now it's neutral. CO3 2- as a base means that it's gaining a hydrogen. So it becomes HCO3. It was -2. It gained a +1 charge. Therefore, now it's -1. NH4 plus is acting as an acid. Therefore, it's going to lose a hydrogen. So it becomes NH3. It was +1. It lost +1. So now it's neutral. H2O loses a hydrogen. So it becomes OH. If you wrote HO, change it. Okay. OH, it was neutral. So now it's going to become -1. Okay. You're gonna have a worksheet tonight. I know I don't not a huge homework person, right? So when I assign it, it's intentional. It will have practice with writing acid formulas. It will have practice going from acid to conjugate base, base to conjugate acid. And then it has 2 little practices drawing the little lines and labeling. Okay. So it's just kind of everything that you learned today that I could possibly assess you on. So if you struggle with the worksheet, let me know. Okay. All right, Ty, have an awesome day.
You too. Thank you.
You bet.
Bye.